Hi everyone. Today in this video we are going to discuss how IR spectroscopy works and what is the principle involved in the IR spectroscopy. First of all, let us start with the IR region. What is the IR region? IR region can be classified based on the wavelength. For example, near IR is going to fall within the wavelength range of 750 nanometer to the 2.5 microns approximately. Similarly, mid-IR is classified as 2.5 microns to the 25 microns and far IR region from 25 microns to 0.1 mm. Among these three regions, the mid-IR region is widely used for the pharmaceutical analysis, which is from the 2.5 microns to the 25 microns. But in the IR spectroscopy, we can measure the absorption in terms of wave number. So this mid-IR region, when it is expressed in terms of wave number, it becomes 4000 to 400 centimeter inverse. So 2.5 microns to 25 microns of wavelength, otherwise 4000 to 400 centimeter inverse of wave number indicates the mid-IR region, which is widely used for the pharmaceutical analysis. So in this video, let us discuss how this IR spectroscopy works and how the vibration transitions can result in the IR absorption. In order to understand the principles of IR spectroscopy, first of all, let us see the Hooke's law. What is Hooke's law? Suppose an object of mass m1 is going to be suspended with a spring and we are applying a force F on the object to the downward direction. Then what happens? The spring is going to oscillate because of the stretching as well as the compression. And suppose here the distance it is going to oscillate is x, then according to the Hooke's law, the force we have applied is directly proportional to the x, that is the distance it is going to oscillate. Now this can be written as F is equal to minus K into X, where K is the proportionality constant and K is also called as force constant. This K depends on the strength of the spring, more the force constant, more the distance of oscillations. In this way, whenever we are going to apply a force on the object which is suspended by a spring, the object will oscillate and the frequency of oscillations can be given by the Hooke's law as nu is equal to 1 by 2 pi into root of K by m1, where K is the force constant and m1 is the mass of the object. Now let us apply the same concept to the two objects which are connected by a spring. And again we are applying a force F on these objects. Now these objects are going to oscillate and again the distance of oscillation depends on the force we have applied. Again here the Hooke's law gives the frequency of oscillations as nu is equal to 1 by 2 pi into root of K by mu. Again the K is the force constant, but what about the mu? Mu is called as the reduced mass. Why it is called as reduced mass? Because we can have an equation 1 by mu is equal to 1 by m1 plus 1 by m2. So 1 by mu is equal to sum of the reciprocals of the mass m1 and m2. Now according to the Hooke's law, when two objects are going to attached by a spring, they can vibrate at a frequency of nu, which is given by 1 by 2 pi into root of K by mu. Now let us apply this Hooke's law in the IR spectra. Molecules will have the different types of chemical bonds. For example, if you take a chemical bond between the carbon and oxygen, these chemical bonds are not rigid, they are flexible and they can act like the springs. So whenever the IR radiation is going to fall on a chemical bond like the carbon and oxygen, it can produce a vibrational transition. So because of this IR radiation, this bond may be either stretched or compressed, so it will vibrate at a frequency given by the Hooke's law. So just like the previous example, here the frequency of vibration nu is equal to 1 by 2 pi into root of K by mu. So K is again force constant and mu is the reduced mass. But here what is the reduced mass? 1 by mu is equal to 1 by m1 plus 1 by m2, where m1 is the mass of the carbon. Carbon is having the atomic mass as 12. Similarly, m2 is the mass of the oxygen, which is having the 16 as the atomic mass. So by substituting this equation, we can calculate what is the reduced mass of the two atoms which are connected with a chemical bond. In this way, Hooke's law can be applied for the molecules which will have the chemical bonds, and these chemical bonds just behave like the springs. Whenever the IR radiation is going to fall, they can be stretched or compressed, and sometimes they can also undergo bending vibrations, and the frequency of these vibration transitions can be given by Hooke's law. But all that glitters is not gold. That means all the vibration transitions may not lead to the IR absorption. We know that vibration transitions are classified mainly into two types. They may be stretching vibrations where the bond length is going to be either increased or decreased, and another one is the bending vibrations where the bond angle is going to be changed. But all these vibration transitions may not be IR active. For example, let us take one diatomic molecule like this. This is the chlorine molecule having the two chlorine atoms. Suppose if the IR radiation is going to fall on the chlorine, it is going to stretch like this, but still it cannot absorb the IR radiation. Similarly, let us take another example of carbon dioxide, which is a linear molecule which is having the carbon attached with the two oxygen atoms by double bonds. And when it is going to stretch or compress like this, again it cannot absorb the IR radiation. So this type of stretching vibration is IR inactive. Then what is required for IR absorption? Let us take one molecule like this. Now here it is having a central atom which is attached with the two similar atoms, and because of the difference in their electronegativities, partial charges are going to be developed. You can observe a partial negative charge is developed on the central atom and partial positive charges on the other two atoms. In this way, the molecule can develop a dipole, and the dipole moment mu is given as Q into D, where Q is the charge that is going to be developed and D is the distance between the two atoms. Now, when the IR radiation is going to fall on this molecule, the molecule can undergo either stretching or bending vibrations so that there is a change in the dipole moment. In this way, IR radiation which is going to be supplied is utilized for the change in the dipole moment, and this change in the dipole moment requires energy which is supplied by the IR radiation. So, for a molecule to absorb the IR radiation, it should undergo a vibrational transition which shows a change in the dipole moment. Now, which type of molecules show IR absorption? So, already we have discussed that for a molecule to be IR active, there should be a net change in the dipole moment. For example, if you take a hydrogen molecule is a homonuclear molecule. So, here two atoms are same and it cannot give the IR signal because of the zero dipole moment. Similarly, if you take the bromine is again having the same atom, so dipole moment is zero. So these types of homonuclear diatomic molecules will not give the IR signal because of the zero dipole moment. Similarly, if you take the case of carbon dioxide is a linear molecule and the dipole moment of the carbon dioxide under resting conditions is zero. Suppose when the IR radiation is going to fall, one of the bond is going to stretch like this and another bond is going to stretch like this. Then again they are going to stretch such that there is no change in the dipole moment. Again the dipole moment is zero. This type of stretching, what we call the symmetrical stretching, where both of the bonds are going to be increased. In such case, it cannot show the IR absorption. So, homonuclear diatomic molecules as well as the molecules with the symmetry cannot give the IR signal. So, molecules which are having the bonds showing the dipole moment can show the IR signal. For example, the bond oxygen and hydrogen is a polar bond which shows the dipole moment. So it can show a IR absorption. Similarly, nitrogen, hydrogen and carbon and hydrogen, all these can show the IR absorption. Similarly, carbon-carbon single bond. Here you can observe that both are same and dipole moment is zero. But still the net dipole moment of the molecule depends on the other groups attached. So carbon-carbon single bond can also give the IR signal because of the rest of the groups attached to these carbons. So these are not the diatomic molecules because carbon is tetravalent, they are polyatomic, and presence of other groups can influence the dipole moment as well as the absorption of this carbon-carbon single bond. Similarly, carbon-carbon double bond can show the IR absorption as well as triple bond can also show the absorption. And carbon-oxygen, which is a carbonyl group, which is in one of the important group that gives a strong peak in the IR spectroscopy. Similarly, carbon-chlorine. In this way, so many types of chemical bonds which exhibit the dipole moments can show the IR signals. Now let us see the frequency of IR absorption. We have already discussed that the frequency of IR absorption is given by the Hooke's law, where mu is equal to 1 by 2.2 root of k by mu. Here the frequency of IR absorption depends on two parameters. First one is the force constant, which is represented by k, and second one is the reduced mass, which is represented by mu. And what is the relation between the frequency of IR absorption and these two parameters? The IR frequency is directly proportional to root of k. That means as the force constant increases, the frequency of absorption increases. At the same time, the frequency of absorption is directly proportional to root of 1 by mu. That means as the reduced mass increases, the frequency of absorption decreases. So these two parameters will influence the frequency of IR absorption. But in the IR spectroscopy, we generally measure the signals in terms of wave number. So what is a wave number? Wave number is the reciprocal of the wavelength, which can be related with the frequency. We know that frequency nu is equal to c by lambda, where 1 by lambda is nothing but the wave number nu bar. So this can be written as c into nu bar. Nu bar is the wave number. Now we can replace this in the equation so that the wave number nu bar is equal to 1 by 2 pi c into root of k by mu. This is just like the previous equation with an extra term c, where c is the velocity of the light in the vacuum. In this way, in the IR spectroscopy, we measure the IR signals in terms of wave number. For example, let us take the case of ethanol. When we observe the IR spectra of ethanol, we can observe the two important peaks. One of the peak corresponding to the OH stretching and another peak is corresponding to the CO stretching. In the first one, oxygen is more electronegative than the hydrogen, and in the second one, oxygen is more electronegative than the carbon. So both of these chemical bonds are having a significant dipole moment, and when the IR radiation is going to fall, there will be a net change in the dipole moment, which results in the IR absorption. Particularly, the OH stretching can be observed at a frequency of 3600 cm inverse, and CO stretching can be observed at 1100 cm inverse. In this way, observing the peaks in IR spectra at different frequencies can give the information about the types of chemical bonds and the structure of the molecule. In our next video, we are going to discuss how this frequency of IR absorption is going to be influenced by two factors like the force constant and reduced mass, and how we can interpret the IR spectra, which is important to identify a particular unknown molecule. So that's for today about the principles of the IR spectroscopy. For a molecule to show the IR absorption, it should undergo a net change in the dipole moment. Hope you have enjoyed this video. If you like this video, please subscribe to our channel, share this video with your friends, post your comments in the comment box. Thank you for watching this video.